Hello everyone. This lesson is on the Fundamental Theorem of Calculus Part 2. Recall that the Fundamental Theorem is named because it links the two branches of calculus, differential calculus and integral calculus. As it turns out, the Fundamental Theorem of Calculus has two parts, each of which relates an integral to an antiderivative. Okay, so let's begin with a function like y equals 3x squared that is continuous on some interval a, b. All right, so let's review the first fundamental theorem of calculus by computing the values in the do now. So if we antidifferentiate the first one, we get t cubed as the antiderivative from 1 to 2, and this would give us 2 cubed minus 1 cubed, which is equal to 7. In the second one, the antiderivative is still t cubed, but from 1 to 3, by the first fundamental theorem, we get 3 cubed minus 1 cubed, which gives us 26. In the next one, the antiderivative is still t cubed from 1 to 4, and we get 4 cubed minus 1 cubed, which gives us 63. So notice that the definite integral is equal to a real number, and this geometrically represents the total net area under the curve y equals 3x squared. But if we generalize this to the definite integral from 1 to x of 3t squared dt, notice that we will still get a function of x. And if we go through the same technique that we did before, the antiderivative is still t cubed, but from 1 to x, where x is some number in the domain of y equals 3x squared, the answer would be x cubed minus 1 cubed, or simply x cubed minus 1. So notice that t is used. We could use any variable, but we deliberately use t because the upper limit of integration here is x. So we wouldn't be confused with what variable we're integrating with respect to. But at the end, we get a function of x. And this function of x represents this function of x, x cubed minus 1, which I'll call capital F of x, represents the total net area under little f of x equals 3x squared from 1 to any number x. Okay, so we say that this definite integral here with the upper limit of integration of x is a function. It comes out to be a function of x, and that function of x represents the total net area accumulated under little f of t dt. Perhaps it would be easier if I call this f of t dt. So let me just correct that so we don't get confused. 3t squared. Okay, all right, so that really is basically the Fundamental Theorem of Calculus Part 2. And what's interesting about this function, the antiderivative, so note that capital F of x, which is the definite integral from 1 to x of 3t squared dt, which comes out to be x cubed minus 1, is a function in itself, and its derivative, well, if we differentiate this, and we get this very, very strange looking expression, the derivative of the integral from 1 to x, which is the derivative with respect to x of x cubed minus 1, gives back 3x squared, which is little f of t dt, little f of t. So, well, little f of t, but the t is replaced with an x. So that gives back f of x. So let's write the the Fundamental Theorem of Calculus, Part 2. Okay, so let's write this down. So Fundamental Theorem of Calculus, Part 2, which really helps us define a new function in using a definite integral. And it says the following. To define this new function, we still have to have little f of x. So let little f of x be a function that is continuous on some open interval I. Then we define a new function. Okay, so all we need is a continuous function on some open interval. We define a new function, and this new function is defined as capital F of x, which is equal to the definite integral from a to x, and instead of writing f of x, we'll write f of t, with the understanding that when we go through the calculus, we'll get a function of x at the end, like we did in the do now. And this new function accumulates area under the graph of f on the interval from a to x. Okay, so this function, we input the x value and out comes the area under f from a to that input. And this is the most important result. Whatever that function is, capital F of x, its derivative, the derivative of capital F, gives back little f of x, the integrand, but we replace the t with an x. Now this is demonstrated in the do now. If we go back to the do now, number 4, notice that we define this function, the definite integral from 1 to x of 3t squared dt in number 4, and that is our capital F of x. And when we go through all of the calculus, we end up with this function, which is capital F of x in its closed form. So we were able to integrate and get a rule for capital F of x. That is the area accumulator under y equals 3x squared from 1 to x. And its derivative gives back the integrand, but we replace the t with an x, which is 3x squared. We should note here that down here, a must be in the interval I, that interval over which little f is defined to be continuous. And of course, x has to be in I as well. Okay, but the lower limit of integration, this lower limit of integration must be in the domain of little f. So this we should not overlook. So let's see how we can prove this. So let's go over a geometric justification of the Fundamental Theorem of Calculus, Part 2. That is to say that the derivative of capital F of x will give back little f of x. And it goes like this. We start with f, little f, to be a function that is non-negative and continuous on a closed interval ab. Then capital F of x is defined to be the area function, which accumulates area under the graph of f from a fixed left endpoint a to a variable right endpoint x. And we could represent it with this integral. we call this the area accumulator. All right, so if we take a look at this, let h be a small number, a small positive number, so that capital F of x plus h, which would look like the definite integral from a to x plus h, remember a is fixed, of little f of t dt, would represent the area under the graph of f from a to x plus h. So let's look at the picture above. So if h, oh, okay, well, let's put both pictures above. So let's say this is the graph of f, and we pick this variable x, and this variable is movable as long as it's within AB. Okay, so capital F of x would represent this area, the area under the graph of little f from a to x. That's the red. The yellow, well, x plus h is a little bit to the right of x, so capital F of x plus h would be the area under the graph of f, little f, from a to x plus h. So it's this area. So when we subtract these two, f of x plus h minus capital F of x, that would represent the area under the graph of f from x to x plus h. And if you take a look at that, we're subtracting this overlap over here. So that would give us this green region. Okay, so let's write that down. Let's write that down. So this represents the area under the graph of f from x to x plus h. Now, to get the derivative in here, we will divide by h. So we're going to divide the f of, okay, this one, I should color code it, is the green one. Okay, so when we take this and divide it by h, because we want to get to the derivative, this is just the area under the graph of f from x to x plus h, all divided by h. Okay, now let's see what we can do with that. Well, when we put the limit in front of this, that's what we need, the limit as h approaches 0, of f of x plus h minus capital F of x all over h. By definition, this is the derivative of f. Okay. Now, when we put the limit here, we have to do something else. The area under f, under the graph of f to x, from x to x plus h, would get, as h gets smaller and smaller, would get closer and closer to the area of some rectangle. So the limit as h approaches 0 of this region okay, so it's the limit of that. Just look at it geometrically. This green region will get so narrow that we could use a rectangle to approximate its area. So let's say that this gets closer and closer to, so, well, let's make a note. Let's do it this way. Okay, I'm going to erase this. let's see if I could erase this. Okay, and let's say that as h approaches 0, the area under f, under the graph of f, from x to x plus h gets closer and closer to the area of a rectangle with the width of h, because note that this here is h up here, if we look at this region here, and a height of f of x. Okay, so let's move on to the next page and see what we get. So going back, the limit as h approaches 0 of the area under the graph of f from x to x plus h approaches the area of a rectangle with a width of h and a height of f of x. And that's written here. So we get the area of that rectangle, but we still have to divide by h. And the h's divide through, and f of x is a constant relative to h. Or we could also think of it this way. Since f is continuous, we could use the definition of continuity, and we get f of x. That limit is f of x. So putting it together, the limit as h approaches 0 of capital F of x plus h minus f of x all over h is equal to the derivative of capital F of x, which is equal to f of x, little f of x. And this is a very important result for the Fundamental Theorem of Calculus, Part 2. Okay, so remember, little f has to be continuous on some closed interval AB, and we define a new function which we will call capital F. We could call it capital I, we could call it G, H, it doesn't matter. A new function which is the area accumulator for little f. And we define it this way. So when the upper limit of integration is x, this has to be another variable, usually t. And whatever x is here, it matches the upper limit of integration, where a is in the interval over which little f is continuous. And whatever that function is, capital F, its derivative, which is the derivative of this integral, gives back little f, but we replace this x for the t. That is the Fundamental Theorem of Calculus, Part 2. It looks confusing, but it's really very simple. I should note that this function we can find usually. We could integrate and find what capital F is as a formula, like we did in the do now. But there are functions out there that are continuous and cannot be integrated. So usually those functions are left in that form here, this form. Okay, let's see how we can apply this. All right, now on this page, I wrote a few problems. The last two, 3 and 4, were multiple choice questions on a previous AP exam. Copy these down and see what you can do with them. Okay, let's start going over this. Actually, these problems are very simple. When we differentiate an integral, we always get back the integrand. But the trick here is to replace the t with an x. And that's really the second fundamental theorem of calculus, or fundamental theorem of calculus part 2. That's what we just talked about. So we rewrite the integrand with an x replaced for the t. That's all you do if we have a derivative of an integral with an upper limit of x. So the answer to the next one would be x cubed minus 1, all divided by 2x cubed plus x plus 1. That's how simple it is. Okay, let's consider now number 3. So capital F of x is the definite integral from 0 to x of sine t dt. We have to get the derivative of capital F at pi over 2. So remember, the rule is differentiate and then substitute. So if we differentiate capital F, we get back the integrand, which is sine x, and the derivative of capital F at pi over 2 is sine of pi over 2, which should give us an answer of 1. So the correct choice is C. In number 4, notice they say x is greater than 1. Okay, so x is some number greater than 1. Notice the lower limit of integration is e, which is in the domain for 1 over t. And the derivative of this would simply be natural log of absolute x, absolute value of x, but because they define x to be greater than 1, we don't need the absolute value. If they didn't do that, we did need it, and the correct choice is B. I wanted to go over with you 2 AP problems dealing with this theme, and it seems like they've been asking this practically every year on the AP. So let's take a look at 1997 AB5. We're given the graph of little f. So keep in mind that this is the graph of little f. This is little f, not anything else. And it consists of a semicircle and 2 line segments as shown above. Let G be the function given by g of x. Okay, so let's just write this out. G of x is the definite integral from 0 to x of little f of t dt. So if we pause a minute, this means that g of x is that function that accumulates area under this graph of little f. Okay, so let's take a look at the next question. All right, part A says, find g of 3. Well, the 3 will be replaced where the x is. So that's the definite integral from 0 to 3 of little f of t dt. We go back to the graph of little f, and we see that from 0 to 3, we're talking about this region, this quarter of a circle, and this little triangle underneath the x-axis. Now remember, the definite integral is net area. So the area of the quarter circle is positive, and the radius is 2, with the center at the origin. So the area of this piece would be 1/4, because it's a quarter of the whole circle. Pi times 2 squared, that gives us pi. And it's positive because that region is above the x-axis. The area of this little triangle here has a base of 1, a height of 1, so the area would be 1/2, 1 times 1, but that would be negated since the triangle is below the x-axis, so that is minus 1/2. And that would be the answer to part A. Now let's take a look at B. B says, find all the values of x on this open interval from -2 to 5 at which g has a relative maximum. So remember, to find out when this mystery function g has a relative maximum, we have to find its derivative. So going back to the definition, the derivative of g is just f of x. So what we have here is the graph of the derivative of g. So this is going back to those old AP problems. Here's the graph of the derivative of a function. Tell me about the function. So to find out the relative extrema for g, we first have to find out when the derivative is equal to 0, which is when f is equal to 0. And the graph of f is equal to 0 at x equals 2 and at x equals 4. Those are the x-intercepts. So now, to find relative extrema, we make a number line from -2 to 5, and that's the domain that they gave us. And we put a 2 here and a 4, and we label our number line with the derivative of g. Okay, let me just write derivative of g here. So we label the number line derivative of g, which is really f. So f, or the derivative of g, is positive in the interval from -2 to 2. That's because the graph of f is above the x-axis, or the graph of the derivative of g. In the same way, from 2 to 4, the graph of the derivative of g is negative below the x-axis, and from 4 to 5, the derivative of g is above the x-axis. So g is increasing, decreasing, increasing, and they asked for relative maximum. Justify your answer. So the relative maximum, g has a relative maximum at x equals 2, because we have to justify, because g, the derivative of g, changes from positive to negative, or you could say the graph of g changes from increasing to decreasing. But focus in on the derivative of the function in question. So that answers part B. Now, let's look at part C. Part C says, write an equation of the line tangent to the graph of g at x equals 3. So this is a very popular question. To get the equation for the tangent of the tangent line to the graph of g, we need the derivative of g at 3, and the point, what the value of g of 3 is. So let's move on to the next page. So when x equals 3, g of 3 is equal to the definite integral from 0 to x of little f of t dt. And I should say this should be a 3 here. And in part A, we found that this is pi minus a half. So the point of tangency is 3 comma pi minus a half. Now we need the derivative of g at 3. Well, since the derivative of g gives back f, right? And we always have to find the general derivative rule before we substitute a number. The derivative of g at 3 is f of 3. And if we look on the graph of f, g of 3 is equal to -1. F of 3 is equal to -1. Okay, and that's just looking at the graph of f. So that is -1. So the equation of the tangent line would be y minus the y coordinate, which is a little different because this y-coordinate has two parts to it. It's pi minus a half equals -1 times x minus the x coordinate. And that would take care of part C. Now part D asks us to get the points of inflection for the graph of f, or for the graph of G. So find all points of inflection, well, the x coordinates at which there are points of inflection for the graph of G. To get the points of inflection for the graph of a function, given its derivative, given the graph of its derivative, which is really f, we have to go back to the graph of f and see in this interval from -2 to 5, when the derivative of G, which is the graph of f, is increasing or decreasing. So we trace f from left to right. So when we start from -2, the graph of f is increasing till 0. From 0 to 2, the graph of f is decreasing. From 2 to 3, the graph of f is decreasing. And from 3 to 5, the graph of f is increasing. And when the derivative increases or decreases, this tells us about the concavity of G. So G is concave up here, concave down, concave down, concave up. And we see that G has points of inflection at x equals 0 and at x equals 3, since G changes concavity. Or we could say the derivative of G changes from increasing to decreasing, or decreasing to increasing. And that would take care of part D. For extra credit, pick a few other points and actually graph G. That's a great extra credit. Graph G, given this information. All right, let's take a look at the next AP problem. Now, this AP problem is similar to the other one, except that we're not given circles and line segments, so we're not able to find the area under this graph of f. This is, again, the graph of f, and capital and little h is defined to be the definite integral from 1 to x of little f. So h accumulates area under f. So now, this, on the year that this was given, this was a BC problem. It was not an AB problem. It was a BC problem. And part A asked us to find h of 1, which was easy enough. So h of 1 is the definite integral from 1 to 1 of f of t dt. And one of the definite integral properties is that when the upper and lower limits of integration are the same, the answer is 0. Okay, so that wasn't bad. Then it asked us for the derivative of h at 4. So first we have to realize that the derivative of h gives back f. In fact, I'll write it out. The derivative of h is the derivative of this definite integral, and by the Fundamental Theorem of Calculus Part 2, that gives back little f of x. So the derivative of h at 4 is f at 4, and if we look on the graph, we see that f of 4 is 2. So the answer is 2. Okay. Now let's take a look at part C. Part C says, on what interval or intervals is the graph of h concave up? Justify your answer. So here, for concavity, we have to look at the increasing, decreasing behavior of the derivative of h, which is f. So we make a number line using the domain that was given up here, 1 to 7, and we describe what f is doing, which is really the derivative of h. So h is increasing from 1 to 3, decreasing from 3 all the way to 6, and increasing from 6 to 7. So h here, the graph of h, is concave up, concave down, concave up. So we could say that h is concave up when the derivative of h, which is equal to f, is increasing, and those are the intervals from 1 to 3 and from 6 to 7. And that would answer that piece. Okay, so let's just put a little box around our answers here. Okay, now let's look at part D. Now, this one was interesting. It said, find the value of x at which h has its minimum on the closed interval from 1 to 7. So if we want to find the minimum on the closed interval, I misspelled minimum, this should be n. On the closed interval, we have to use the closed interval test. Okay, so that was the little twist that year. Let's see how we would do that. So in part D, we have to use the closed interval test. And before we use the closed interval test, we have to use the closed interval test on h of x, on the interval from, 2 to 7? Excuse me, 1 to 7. So the first thing we have to do is we have to set the derivative of h to 0 to find critical values where there may be a relative max or min, but we have to substitute these back into h. And the derivative of h is little f. And we set that to 0. And we see that f is equal to 0. The graph of f crosses the x-axis at x equals 5. So we use the closed interval test on h. Okay, so this was very different that year. So we have to put the 1, the 7, and the 5. So this integral would translate into the definite integral from 1 to 1 of little f of t dt. But we know that's 0. Okay, this would represent the definite integral from 1 to 5 of little f of t dt. And the best we can say is that because the graph of f looks something like this, we know that the area under f from 1 to 5 is certainly greater than 0 because that piece is above the x-axis. Now, if we take a look at at 7, we're looking at the definite integral from 1 to 7 of f of t dt. And here, to find the answer, we can't find a numerical answer, but we could discuss the sign. Well, since the area under f from 5 to 7 has to be less than 0, since the graph of f is below the x-axis, however, if we add that to the definite integral from 1 to 5 of f of t dt, plus the definite integral from 5 to 7 of f of t dt, this is negative, this is positive, and the sum of a positive and a negative could either be positive or negative. But our result would be positive because there is more. Okay, so this is greater than 0 because there is more there. Oh, let me just write that clearer. There is more area under f, under the graph of f, from x equals 1 to x equals 5 than the area under the graph of f. And always identify your function from x equals 5 to x equals 7. So this is still positive, but it's less positive than the integral in the middle. So to answer the question, the absolute minimum should be at x equals 1. Let's write that down. The absolute minimum of h is at x equals 1 with a minimum value of 0. Okay, because at x equals 5, we see that h is positive, and h is also positive at x equals 7, but h is more positive at h equals 5 than h equals 7, meaning that h of 5 is more than h of 7, but that doesn't matter. They're both positive numbers, and 0 is always less than positive numbers. So that's the absolute minimum. The absolute maximum here would be at x equals 5. We don't know what the absolute maximum value is, but we know that it's more than whatever the value of h is at x equals 7. Before we go, let's take a look at the TI Inspire. Okay, so I wanted to show you the graphical interpretation of what we've been doing. I graphed y equals the natural log of x in f1, and in f2, I looked at, let's see if I could get to f2 here. Okay. And f2 is defined to be the definite integral from 1 to x of 1 over t dt. This is the way to define the natural log function in terms of a definite integral. Because if we go back and evaluate this integral, we get the natural log of the absolute value of x. And if we substitute x and then 1 into that antiderivative, we would get the natural log of x. And if we graph that, it should overlap the blue graph. So let's do that. And let's just escape here so we could see. And notice that the blue graph and the red graph overlap. So this is the direct definition of the natural log of x, and this is the definition of the natural log of x in its open form. We say this is the closed form. Now, when we differentiate f2, so let's go back to this, see if we could get to f3. If we differentiate this definite integral, it should give back 1 over x, which is the hyperbola. And when we graph that, you see that the black graph is the hyperbola 1 over x. So that's a nice demonstration of the fundamental theorem of calculus, part 2.
And that concludes our lesson.
So everyone take a look at the problems we've done together and study them, because they are bound to ask a question like this on our upcoming AP exam. All right, have a great day, everyone.